Good morning, students. Today we are going to discuss the topic of isotope effect in rotational spectroscopy. If the isotope of an element changes, its mass changes. As a result, the moment of inertia changes because rotational constant, that is beta or B, is related to the moment of inertia by equation B is equal to J divided by 8 pi square IC. So B is inversely proportional to I. Due to the change in the moment of inertia, the value of B changes, and so the position of spectral lines in rotational spectra is also changed. This effect is called as isotope effect. If the isotope has higher mass number than the previous one, moment of inertia increases, hence B value decreases. So it absorbs at lower wave number. It is important. For example, the spectral lines in DCL will be obtained at lower wave number compared to SCL, because in DCL D is for deuterium and mass of deuterium is higher as compared to mass of your hydrogen. Because of that, moment of inertia changes. Due to that, we see that beta is inversely proportional to your moment of inertia. As the value of I increases, value of B decreases, and because of that, in a rotational spectra of DCL, we got lines at lower wave number compared to SCL. Now we are going to see application of rotational spectroscopy. An important application of rotational spectroscopy is indetermination of moment of inertia and bond length of various molecules. Rotational spectrum of diatomic molecules show equally spaced lines at separation of 2B. The value of B is related to moment of inertia by this formula, that is B is equal to H divided by 8 pi square IC. Knowing the value of B, that is the rotational constant, one can calculate moment of inertia. Since all the other parameters, that is H, 8 pi square and C are constant, I, that is moment of inertia, is related with internuclear distance. It is important by the formula I is equal to mu R0 square, where mu is reduced mass of your system. From the value of I and atomic masses of the bonded atom, one can simply calculate R0, that is bond length of the molecule. Also, it is possible to calculate both the bond lengths in triatomic molecule using the phenomena of isotope effect. Now we are going to see some numerical based on rotational spectroscopy. But before going for numerical section, student should know some conversion factor. We know that 1 meter is equal to 100 centimeter. So 1 centimeter can be written as 10 raised to the power minus 2 meter. If we have to convert 1 centimeter inverse into meter inverse, then 1 centimeter is inverse is equal to 100 meter inverse. How it is written? Just see, centimeter inverse means 1 divided by centimeter and 1 divided by meter. Just cross multiply, we got our original condition, that is 1 meter is equal to 100 centimeter. So student should note that the conversion factor for centimeter inverse is equal to 1 centimeter inverse is always equal to 100 meter inverse. So let's consider a small example. We have to convert 12 centimeter inverse into meter inverse. So just multiply 12 with 100 meter inverse divided by centimeter inverse. So it is simply 1200 meter inverse. Now if a molar mass is for hydrogen given 1.008, so molar mass always divided by Avogadro number. So now we are going to see for numerical. The microwave spectrum of HI molecule consists of series of equally spaced lines at 12.8 centimeter inverse. Calculate moment of inertia and bond length if a molar mass are. For hydrogen it is 1.008 and for iodine it is for iodine it is 127. So what condition first we have to write given. So in this numerical, delta mu bar value, that is size B, equally spaced line, is given, that is 12.8 centimeter inverse. We have to convert this centimeter inverse into meter inverse. So just we know that 1 centimeter inverse is equal to 100 meter inverse. So multiply this value by 100. Molar mass of hydrogen is given 1.008. First this mass is converted into kg. It is given in gram mole inverse. So for converting gram into kg, multiply this quantity by 10 raised to the power minus 3. It is the molar mass. Divide molar mass by Avogadro number. So we comes with 1.67 into 10 raised to the power minus 27 kg. For iodine, M2 is given as 127 gram mole inverse. Multiply 127 with 10 raised to the power minus 3 and divide it with Avogadro number. So it comes as 211 10 raised to the power minus 27 kg. Value of size B, that is equally spaced line, is given, that is 1280 meter inverse. So we simply calculate B, that is equal to 640 meter inverse. We know that the formula B is inversely proportional to your moment of inertia. So B is equal to H divided by 8 pi square IC. H is a Planck's constant. C is velocity of light. Just put all the value in this equation. He comes with value of moment of inertia. So moment of inertia comes as 4.37 into 10 raised to the power minus 47 kg meter square. Now we have to find bond length. So we know that moment of inertia is equal to reduced mass R0 square. So we rearrange this equation for R0 square. The R0 square is equal to M1 plus M2 divided by M1 M2 multiply by moment of inertia. Put all the values. So R0 square value, that is bond length square value, is 2.637 into 10 raised to the power minus 20 meter. Take under root. So R0 value, that is bond length value, is 1.624 into 10 raised to the power minus 10 meter. Convert this meter into Armstrong. So bond length comes as 1.624 Armstrong unit. Now we are going to solve second numerical. The rotational constant value of NO is 1.66 meter inverse. That is, value of B is directly given. Calculate bond length in NO molecule if it is reduced mass is 1.24 into 10 raised to the power minus 26 kg. So mu value is also given, B value is also given. So first, by using the formula B is equal to H divided by 8 pi square IC, we calculate moment of inertia, which is come as 1.687 into 10 raised to the power minus 46 kg meter square. By using the formula of moment of inertia, that is I is equal to mu r0 square, we rearrange this formula for bond length, that is r0 square is equal to I divided by mu. Value of reduced mass is directly given, put that value into this. So we comes with 1.36 into 10 raised to the power minus 20 meter. Take the square root. So r0 is equal to 1.166 into 10 raised to the power minus 10 meter. Convert this meter into Armstrong. So we comes with 1.166 Armstrong unit. Now we are going to see third numerical. The microwave spectrum of HCl molecule shows equal space line at 20.80 cm inverse. Calculate internuclear distance between hydrogen and chlorine. Molar masses of hydrogen and chlorine are given. So equal space lines, that is delta mu bar is equal to twice B, that is equal to 20.8 centimeter. Convert centimeter inverse into meter inverse by multiplying with 100. So it is comes at 2080 meter inverse. Now convert molar mass into kg by dividing with Avogadro number. Now molar mass of hydrogen is divided by Avogadro number. This 10 raised to the power minus 3 is convert this gram into kg. Same thing is done here for chlorine. So value of times B is given. From that times B value, B easily calculated. So from this B, we can easily calculate moment of inertia. Just put all the values in this formula. I comes as 2.69 10 raised to the power minus 47 kg meter inverse. As we got the value of I, so we simply calculate bond length by using this formula. So I is equal to mu r0 square. So r0 square is equal to m1 plus m2 divided by m1 multiplied by m2 multiplied by your moment of inertia. Put all values in this formula. So r0 square, that is bond length square value, comes as 1.65 10 raised to the power minus 20 meter. Convert this, take the square root. So its value comes as 1.29 10 raised to the power minus 10 meter. Convert this meter into Armstrong, that is bond length comes as 1.29 Armstrong. This is the numerical or a short question which is generally asked in the exam. This question is basically based on selection rule. Which of the following molecule shows rotational spectra and why? So these are some molecules are given, and we have to decide out of this molecule which molecule give rotational spectra. According to selection rule, rotational spectra is given by those molecules which have permanent dipole moment. So hydrogen in gaseous form, this hydrogen does not have permanent dipole moment, that's why it don't give rotational spectra. Same case with your N2 gas, same case with your Cl2 gas, because they don't have permanent dipole moment. HCl in gaseous form, it have permanent dipole moments as del positive and del negative. So this molecule give rotational spectra. HR is also give rotational spectra. CO in gaseous form also give rotational spectra. Same case with your NO, because they all have gaseous state as well as permanent dipole moment. Now just see ammonium chloride. Ammonium chloride have del positive and del negative permanent dipole moment, but this molecule does not give rotational spectra because in a numerical state of ammonium chloride given as solid. Rotational spectra is obtained in gaseous form, not in solid form. That's why this molecule, though it have permanent dipole moment, but it is present in solid form, it does not give rotational spectra. In our next class, we are going to discuss vibrational spectroscopy. Thank you very much.